A quick ask before we start the episode. We have a survey, a very brief survey that we would love for you to fill out. There's a link right there in the show notes. It'll help us learn a bit more about you and what keeps you downloading the shows so we can create the best possible stories that connect to your interests. And as a thank you for completing the survey, if you leave your email at the end, you will have a chance to win a $100 Amazon gift card. Thank you so much for listening and for filling out the survey.
From the studios of Postscript Media and Canary Media.
I'm Shayle Khan, and this is Catalyst.
We started our company in 2018 specifically because you could do some really simple arithmetic and come to the realization that a critical bottleneck for the electric vehicle revolutions and the energy transition more broadly would be the supply of these key materials.
Lithium, nickel, cobalt, copper. If you don't already know why we need to talk about them, do you even climate tech, bro?
Let's face it, environmental news is often very depressing. That's why we focus on solutions on this podcast. But still, the climate crisis looms large. Rising temperatures, mounting pollution, environmental degradation, they're all warping the planet. And for a lot of species, including us, things don't always look so great. But the story doesn't end there. Every Friday, Living Planet, a show from Deutsche Welle, takes you behind the headlines to figure out what's happening and how we'll get through it. It'll also help you make better choices for a healthy planet and find space to reconnect with the beauty and wonder of the world around us. You can find Living Planet wherever you get your podcasts.
I'm Shayle Khan. I'm a partner at the venture capital firm Energy Impact Partners. Welcome. So first, a reminder, as you heard last week, if you listened to the episode, we're going to try and Ask Me Anything episode, sort of a mailbag kind of thing, where I answer, or at least attempt to answer, all of your big and small questions about the world of climate tech. If you want to ask a question, just tag us on Twitter or on LinkedIn with the hashtag AskCatalyst. That's hashtag AskCatalyst. We are going to go through all of them and answer as many questions as possible, so don't hold back. And stay tuned for the episode in coming weeks. Okay, on to today. So I'm looking at a report of price changes for commodity metals in 2021, as I am wont to do. There are over 50 different metals listed on here, so it's all across the board. Some were up. Copper rose 26% last year. Some were down. Silver went down 12%. But on the entire list, the biggest price increase was for lithium, both lithium bicarbonate and lithium hydroxide, the two different formulations used in lithium-ion batteries. Prices rose between 300 and 400% in both cases last year, and they've only gone up so far since then. And it's not just lithium. Cobalt, which is another key battery metal, rose close to 80% last year, and it's really only gotten crazier since then. There's been some madness in nickel markets this year, and it's just a really big problem for electrification. We're seeing battery prices increasing in part because of this today. Meanwhile, we've just started to see this question of how are we going to resource all the minerals needed for the battery revolution and the energy transition come to the fore in the mainstream press. We've seen auto OEMs racing to lock up supply deals for key minerals as they roll out new EV models. The market value of both public and private companies with mining assets or new technologies to unlock them has skyrocketed. Elon Musk just tweeted about lithium prices last week. So what's actually happening here? Will battery metals supply become the bottleneck to electric vehicle adoption? Will a new wave of development restore balance as the market expands? Which of these metals are really a problem and which ones are not? And how will that be affected by changing battery cell chemistries, which will impact the demand for individual metals? This is, in my opinion, going to be one of the biggest through lines of the next decade in climate tech, and it's a lot to unpack. Fortunately, my friend Kurt House is here to walk through it with us. Kurt is the CEO and co-founder of Cobalt Metals, which is using AI to discover and characterize new sources of key battery metals. We'll talk more about which ones. When I asked Kurt to have this conversation with me, Kurt promised to, and I quote, wonk the shit out of me, which, if you know me, is the most beautiful music to my ears. So here we go. Kurt, welcome to Catalyst.
It's great to be here, Shayle.
I've been wanting to have a conversation with you about battery metals for a long time, and it's taken us a while to finally get this done. So I'm excited to do it. Let's start at the high level. Walk us through like what minerals matter today the most as it pertains to battery chemistries.
We like to think about basically five key sort of renewable energy and battery materials. Those are copper, nickel, lithium, cobalt, and the rare earth elements. Aluminum is kind of a sixth, deep sixth one as well. Because long. But let me go through those in turn and talk about the sort of critical application for each of them, and importantly, why it's so difficult to substitute any of those for some new material. So let's start with the workhorse of the energy transition, and that's copper. Copper's a big global market right now, very big. It's an order $100 billion market. It's sort of one of the key metals markets. It is the principal electron carrier in basically all electricity applications, right? From everything in your EV, where the electrons are moving around outside of the battery, to distribution wires, to wind turbines, to the motor in your EV and every electric motor. In some sense, what an electric motor really is a bundle of copper wire surrounding a permanent magnet, or surrounding a different bundle of copper wire in the form of an induction motor. An EV, as you probably know, requires about 3x mass of copper than an equivalent internal combustion car. It's a big market, but it has to grow much more rapidly than it has in the past to fully transition the economy. By our estimates, we need roughly $5 trillion of new discoveries of copper, and we'll come back to what I mean by discovery. Let's keep going. But new discoveries of copper just to fully electrify the light-duty vehicle fleet, not including all the renewable energy build-out and electricity distribution. The next key material is lithium. This won't be a surprise to your listeners because we call them lithium-ion batteries for a reason. But why do we call them lithium-ion batteries? Because lithium is not the only element in those batteries. So a battery is a combination, you could think of it, to slightly oversimplify, of three different components. An anode, an electrolyte, or sometimes called a separator, and a cathode, right? And the anode is where, when you're discharging a battery, i.e. you're using your phone, you're driving your car, the electrons leave the anode, and so does a positive charge, so that you're always in charge balance. Lithium is the anode material, or the active anode material, and it's the mobile atom. It's in a battery. The only things that move are electrons and the lithium nucleus, right? The lithium atom. And so when you discharge your battery, the lithium atom migrates across the electrolyte, and the atom goes through the circuit, and then they recombine in the cathode. Lithium is remarkably better than the next best anode material. Shockingly better, actually. It's kind of a miracle of the universe, and it's really easy to understand this. Actually, lithium is. Do you remember what the atomic number of lithium is, Shayle?
I don't. Why don't you remind me?
Okay, well, that's really important because it's 3, which means it's the third. There's 3 protons. It's the third lightest element. It's the lightest metal. It's also the most electropositive metal on the periodic table. Second most electropositive element, period, which means it wants to give up its electrons. It doesn't like its electrons. You'll remember that from high school chemistry. It wants to give them up. It's super light, and it really wants to give them up. What that results in is in really nerdy speak, we would say a high free energy of reduction. But that really means that as it loses its electron, you can get a lot of energy out of that because it wants to be in a state of not having that electron. So it's really light and it's really potent. The electron leaves with a lot of energy. Okay, now where does that electron go? It goes to the cathode.
So
your next
let's distinguish
materials-
lithium from copper for a second then, because as you mentioned, copper is a really big existing market, lots of applications that have been around for a long time. Lithium's a different story, right? Where the size of the existing market prior to vehicle electrification or prior to the rise of lithium-ion batteries outside of consumer applications is a much smaller current market, right? So the trajectory of growth is a little different.
Totally, it's a fantastic point. Fantastic point, Shayle, and you're spot on. So here's a good way to think of it. Copper current total mine production is 25 megatons a year or something like that. We think it needs to grow by mid-century, including other uses, to something like 60 megatons a year. So it sort of has to double, right? Lithium, and a big chunk of the growth, not all of the growth, but a big chunk of the copper growth is the energy transition. Lithium, so if you go back just like 22 years, and I know you're old enough to remember the year 2000, Shayle.
Thank you very much.
The number one, the principal use of lithium in that year was lubricants, additive to lubricants, right? It's a very small market, idiosyncratic market. Lithium is a brand new need, and the need is stunning. So current lithium production is right around, I'm doing this from memory, but it's right around 150 kilotons, something like that.
Just for folks who aren't familiar with the terminology, then that's like 20x difference. Is that one order of magnitude, or that's two orders of magnitude?
Yeah,
right.
It's order 100 times less mass of lithium is produced every year than copper is produced. Now, it doesn't have to go up, but it has to go up to, by mid-century, something like 2.5 megatons. So it has to grow by over an order of magnitude, a factor of 30 or something like that, depending on your estimates, as opposed to doubling. So it has to grow just staggering amounts because, exactly as you say, there's the baseline market isn't there because there wasn't a need for it. So lithium, we face, it has two very, very interesting components to it. One is that it's virtually impossible to substitute for because a better way to think of it is this: the drop from the best anode material is lithium by a long shot for the reasons I just described, really fundamental physics. The second best anode material is sodium, and it is way less good. And it's easy to understand why, because the molar mass is 3 times, and it's less electropositive. So there's less you get less energy out per electron, and it weighs 3 times as much, right? So it's far, far, far less good. It's decent. It'll work in certain stationary applications where energy density isn't a premium, but for mobile applications and commercial electronics, it's far, far less good.
We'll come back to some sort of evolution of battery chemistry in the future, because we could talk about, I don't know, stuff like silicon anode and things like that. But I want to let you finish the top 5. So we got to copper and lithium. What's next on the list?
One more point on lithium, just to keep it in context. So it has to grow by a factor of 30 or more. But the total value of the new discoveries, we'll come back to that D word later, but the new discoveries is about 3 trillion, or maybe 4 trillion as opposed to 5 trillion. So it's actually on the same order. The market opportunity for new lithium discoveries is about the same order of that as copper, which is actually a really important point, and it has some interesting implications for market structure and what the incumbents are doing, which we'll get back to, I'm sure. So the next two, and we'll talk about these in pair, is nickel and cobalt. These are what happens when the electron reaches the
this is the cathode.
The cathode.
This is what goes in the cathode.
Exactly. You can think of an like your iPhone, or you can think of it. Yeah, you can think of your iPhone. The reason it works is because there's a chemical reaction between lithium and cobalt oxide. In your iPhone, there's no nickel, and I'm going to explain why in a second. It's lithium and cobalt. The key, there's several key and very somewhat technical points here as to why nickel and cobalt, why nickel and cobalt are so good. But I'll give kind of a simple explanation. So the first is how much they want to take electrons, right? Lithium wants to give them up, right? So that's related to their electronegativity. But they also, and this is really important, they need to form a stable crystal structure with lithium. And that crystal structure needs to remain stable whether lithium is present or not. Okay? When you're charging your phone, what you're actually doing is you're pushing lithium out of the cobalt oxide crystal back onto the anode. And so like a fully charged battery, right? You fully delithiate the cathode has almost no lithium in it. It has about 10% in it for structural reasons. But the point is, as you're removing atoms from that crystal, if that results in a phase change, meaning the crystal starts to change structure, that's really, really bad because those changes can be irreversible, and that's how you get to sort of catastrophic losses in battery capacity. So what's really important is they form stable crystal structures with lithium, right, in a sort of stoichiometric ratio between lithium and cobalt, and that they want those electrons, that the overall net reaction going from lithium to lithium independent of cobalt oxide to lithium cobalt oxide combined is downhill. It's very favorable. So cobalt's the best to do that, and nickel is a reasonable second, a fairly close second. And there's just a huge drop to the third best cathode material, and that's probably iron phosphate. You might make the case that it's manganese oxide, and we can talk about both of those if you like. And
yeah, so just to for folks who've heard this terminology and like haven't thought a lot about it, right? You said the copper is the workhorse of the energy transition. I think the workhorse of cathode chemistry currently is NMC 811. NMC being including N, which is nickel, and C, which is cobalt. And then you mentioned the sort of next best being iron phosphate. The sort of there's been a transition, particularly for stationary storage applications, and some talk, particularly in China, around for lower end EV models of switching to lithium iron phosphate, which is LFP batteries. So that when you hear NMC and LFP, that's what that's referring to.
Yep, totally true. And let's talk about why we talk about nickel and cobalt together. Cobalt is better than nickel kind of across the board on a performance basis. But nickel has one dramatic, two very material benefits over cobalt. And the first is price. These are not totally orthogonal, but the first is price. Cobalt currently is about $80 a kilogram. Nickel's about 30. And the ratio has been a kind of a steady 2.5 to 3 over the last 15 years, the nickel over cobalt price. The reason for that is there is more existing supply, and most importantly, the supply is more diversified. Cobalt has a very highly concentrated supply in the Democratic Republic of Congo, about 2/3 of existing production. So the rate at which cobalt's coming out of existing mines, and 2/3 of reserves, the total amount of cobalt, the total amount of cobalt in the ground that we know can come out in an economic fashion, is in the DRC. The DRC is a very troubled jurisdiction for all kinds of reasons, which we can get into if you like. But nickel's produced in dozens of countries: Indonesia, Canada, Australia, Finland, Norway, Russia, which is a problem. We can come back to that. Russia's the number 2 nickel producer in the world. It's also the number 2 cobalt producer in the world. So the nickel and cobalt kind of trade off. I've got a question for you, Shayle. In your phone, it's only cobalt in the cathode. In your EV, and I assume you drive an EV, you're exactly right. It's going to be either NMC, nickel manganese cobalt cathode blend, or it's going to be NCA if you have a Tesla, nickel cobalt aluminum. So why is that? Why is there that difference in battery chemistry between your phone and your car?
Why is there no nickel in my phone, but there is in my EV battery? I don't know. You tell me.
Okay, so the answer is that your phone costs something like $1,000, and the amount of cathode metal in your phone, cobalt, costs 50 cents, something like that. So Apple, when they're designing their battery, they make the absolute best battery possible for the specific performance that they're looking for, which has a variety of specs. In your car, you will have a lot more battery metal. You'll have a few $1,000s of battery materials, right? And so if you double the price of cobalt, you add 30, 40, 50 cents to the cost of your phone. It doesn't matter. Performance matters. If you double the cost of cobalt and you're using cobalt only in your car, you will add thousands of dollars to the price of the car. And that really matters in terms of demand elasticity. So what you start to do is you start to titrate between the two. It's a performance cost optimization. And a blend of nickel and cobalt can perform really, really well, almost as well as a pure cobalt battery. And the demand, the specifications are slightly different between the two, but overall, that's the principal reason.
Okay, so let's round out the top 5. So we've done copper, lithium, nickel, cobalt. Name the last one.
Yeah, so the last are the rare earth elements. This is actually a set of materials that are used for a variety of things. Most importantly for this conversation is that they make powerful permanent magnets work, and those are how electric motors work chiefly. Those are actually less of a supply challenge than the others. Actually, it's more of a sort of a geopolitical challenge and an environmental impact challenge. I mentioned aluminum quickly, and that's because long distance transmission lines use aluminum because it's cheaper. It's cheaper than copper, but it has about 60% the conductivity of copper. Copper is the third most conductive element, but the only two elements that are more conductive are gold and silver. And for obvious reasons, we don't want to use gold and silver in our electrical wiring.
Utilities have been accused of gold plating their systems, but not in a literal sense, generally speaking. The other thing with aluminum, by the way, is like aluminum is a lighter weight structural metal than iron is, than steel. So it's good for lightweighting electric vehicles or planes and things like that. So it's got tailwinds there. Yeah, I as I started to learn about this stuff, I was also surprised. It's like counterintuitive, the idea that rare earth metals are actually like less of a general supply constraint than they're literally called rare earth metals, but where they come from matters a lot.
They're called rare earth because their relative abundance in the Earth's crust is low. But that on its own doesn't tell you much about the supply and demand dynamic. There's sufficient identified in reserves that we don't actually need new discoveries of it. It's just that most of that is in China or Vietnam, and so there are sort of supply, some supply concerns. Also a challenge. There's plenty of reserves elsewhere. The problem is the processing of the stuff is relatively nasty and intense, and it's been it's made it very, very difficult to develop those mines in Western countries. The processing of these other four materials we just talked about is a lot less intense.
I want to come back to lithium and nickel in particular, and you can tell me if this is true of cobalt as well. I've just paid less attention there. It's been a wild ride for the past 12 months or so in those markets, and I'm sure lots of folks are familiar with hearing about how lithium prices, lithium carbonate, and lithium hydroxide prices have shot through the roof. Elon Musk tweeted about it recently, so probably a lot more people know about it.
Then.
Yeah, gotta be interesting. But I mean, nickel might be even crazier, right? The London Metals Exchange had to shut down for a minute because nickel prices went through the ceiling, and there's some crazy trading activity there. So, what the hell's happening? Like, why are all of a sudden, given that we sort of have been able to watch this vehicle electrification transformation, the electrification of everything, it didn't show up overnight. So, what happened in these markets that are driving them insane?
Yeah, no, it's a super good question. I mean, I think if you do look from a wider lens, temporal lens, it is quite predictable. It's why we're in the business we're in, right? We started our company in 2018 specifically because you could do some really simple arithmetic and come to the realization that that a critical bottleneck for the electric vehicle revolutions and the energy transition more broadly would be the supply of these key materials. And in fact, the price of nickel has been moving up very steadily for the past 4 years. When we started the company, I think nickel was about $8 a kilogram, and now it's over 30. Lithium has been volatile for sure. It is it's had a very dramatic spike over the last 6 months, and I'll speculate a little bit on the cause of that spike. The nickel craziness in the nickel market that you refer to is acutely related to Russia. Russia, as I mentioned, is the second largest nickel producer behind Indonesia. But here's the key: is that Indonesia is really a high-cost producer. They produce out of a type of deposit called laterites, which are almost like metallic dirt, low concentration, kind of high processing costs. It costs $15, $20, $25 a kilogram to process that. Almost all the nickel coming out of Russia comes from the Norilsk complex in Siberia. That is by far the lowest cost producer of nickel in the world. They sit on the far left-hand side of the supply curve. And actually, depending on how you look at it, you could argue that their cost of nickel production is about negative $10 a kilogram. The reason you would say negative is because they produce about 40% of the world's palladium out of that deposit. And the palladium alone would pay, if hypothetically they had to pay people $10 to take away their nickel, they would still have a profitable operation from the sale of palladium. That's obviously not what happens. They get market prices for everything, but it's a crazy low. It's a remarkable sort of deposit, remarkable geologic event there. That resulted in it. And so it's about 15% a little less than 15% of the world nickel production, but it's the cheapest 15. It's the lowest cost stuff. Those supplies haven't actually been disrupted yet, although I think you can make a strong case that they should be, which maybe we talk about. What happened in the LME was a bit parochial, actually. It was that all commodity prices started to spike because of expectations that supply from Russia would be curtailed, and so various traders were buying up any lots they could get. There was a hedge fund out of Chinese hedge fund that had a very metal tradings group that had a very short nickel position, and they were massively exposed. So it was a short squeeze that sent it over $100, which was why the LME shut down. But it's back down to about $30 a kilogram now, which is about $6 above where it was prior to the Russian invasion. At $30 a kilogram, and this is important, right? Like, these prices will not. I would bet against nickel being at $30 a kilogram 2 years from now, because 2 years ago it was less than 20, and there were plenty of good projects out there, new projects that would work at 20. There's a huge number of good projects that will work at 30. Like nickel, it's very in the money if you're a nickel property developer right now. And so, the old adage, right, that the cure for high prices is high prices. That's certainly going to be at play in the near term. The bigger issue that I think we're focused on, and the world should be focused on, is we need total nickel production to grow by a factor of 4 or 5 by mid-century, and that's a rate of growth that is unprecedented in that market.
Right. Yeah, that's a really key point, is that in the nickel context, and then we should come back to lithium, because I know you're going to talk about what's been happening there too. But in the nickel context, it may be that in the short term, meaning the next few years, there actually is sufficient supply to turn on to meet demand. Prices may stabilize, go back down even a little bit, and it's going to look like we don't have a nickel crunch if you're looking at it in a snapshot view. But in the longer term context, we probably still do have a nickel crunch, and hence your need for new discoveries. Let's talk about what's happened in lithium briefly, compare it to the nickel thing, and then let's talk about what's actually needed in terms of new discoveries.
So it's actually I'm not sure what's happening in lithium in the shortest term view, to be honest. It's the long term, we're extremely bullish on lithium, and actually bullish is the wrong word to say. We are confident the lithium price will stay, elevated in the long run, not related to the current spike, but just in the long run, elevated because there will be constant demand pressure, and in fact, I'm sort of concerned about it. I think it will be a governing. I am concerned about it, very concerned about it. It'll be a governor on the rate of the energy the pace of the energy transition. Most recently, this is definitely my speculation. So you'll probably get some nasty blog posts saying that I'm totally wrong here, which I would welcome, because I'd welcome other speculation. But I think what's going on is the following: we've had a lot of growth in lithium production out of high concentration brines. There are effectively three. Crudely speaking, there are three categories of lithium deposits. This is crude because the tighter you look, the more tightly, the more you can segment it. No two deposits are the same. But crudely, you can say there's brines, which is salty water in the subsurface that you pump to the surface, and then you separate out the ion that you want that's dissolved, in this case lithium. There are pegmatite formations, which is often called hard rock, which is a mining operation with a high concentration of lithium. And then there are clay deposits, which are rather than of a sort of volcanic origin, they're more like a highly weathered sediment rock. The clays are not really a source of lithium today. There are people speculate about them becoming a major source. There's lots of lithium in clays for sure, but it's very expensive to process it. So it's not obvious when they'll come into they'll come into the fold. But the growth over the last decade has principally been supplied by brines, and there was a sort of market expectation that brine growth was that there was a large inventory of brine growth. The brines could sort of continue to supply, to feed the growth sort of relentlessly.
And this is predominantly South America, like
yes,
Atacama and Chile,
correct,
and Bolivia.
Yeah, exactly. Yeah. That's right. And there's some brines in China. There's some brines in Eurasia, elsewhere, that are high concentration. But what do we mean by high concentration? We're talking about like more than 500 parts per million, even bit more like closer to 1,000 parts per million. That's what we talk about high concentration. If you do a histogram of brine, lithium concentration in brines, right? You will have a sort of Pareto distribution where a very small fraction of lithium in brines is over 500, 600 ppm. And actually, you'll find this interesting, Shayle. Just plot where the brines are in the world, the producing brines, the high concentration producing brines, the existing producers. Plot where they are in the world, and then look at it on elevation contours. And what you'll find is they're all very high elevation.
Super high
yeah. Elevation. And the reason for that, this is easy to understand, actually. The reason is at those high levels, you actually have greater evaporation, evaporation of the various groundwater sources, and which leave, as you're evaporating water and leaving behind the stuff that's dissolved in the water, the concentration increases. So sort of nature helps you with that process. So there was kind of strong expectations that there would be that we would just kind of continue to add to that supply, because that's where things had gone. I think there's been a market realization that growth there is going to be much more curtailed, because it's a very idiosyncratic set of circumstances that result in those very high concentration brines. There's gargantuan amount of lithium in low concentration brines. If you're willing to produce at 10, 20, 30 parts per million, which you could do technically, no problem. All right, you can get lithium out of that concentration. The problem is it just costs a lot of money, right? For obvious reasons. You're processing that. If you go from 500 parts per million to 25 parts per million, you're processing 25 times as much water for every 20 times as much water for every unit of lithium that you produce. There's gobs of lithium dissolved in the groundwater. It's just it's particularly unique circumstances that give rise to these super high concentration brines, you've just seen a slowing of new supply from that source. You've also seen you've seen rumblings from Chile in particular about nationalizing their lithium supplies and things like that. And that of course is giving lots of people concern. So traders are out buying lots of lithium as fast as they can in an expectation that supply is exceeding demand in the near and medium term.
Okay. So let's transition to talking about the future a little bit here. You Cobalt, the business that you co-founded, is in the business of doing a better job of making new discoveries of all of these minerals that we've been talking about. And so you've developed a strong view on what discoveries we will need based on what the demand will be. Underpinning that, I guess, has to be a view on what battery chemistries win out, right? Because there will be presumably some transitions in battery chemistries, and we sort of alluded to some of this, right? But there are folks who are pursuing alternatives to lithium in the anode. There are folks who are pursuing alternatives to nickel and cobalt in the cathode. What do you think is the sort of future trajectory of battery chemistry? And then what does that mean in terms of what we need to discover in order to supply all of that?
Yeah, no, it's a super good question. So we should go through those kind of again, maybe from a slightly different angle. But the reason I sort of harped on the challenge of substitution for lithium is that it's really built into the universe. Like lithium is the best atom for the best anode material for really, really deep reasons. There's not another element out there that happens to be the lightest metal and the most electropositive metal, which also happens to complex very effectively with transition metals in stable layered oxide crystal structures. Like there isn't one. We know this. We understand the periodic table fairly well. And that, techno-optimists roll their eyes at stuff like that because they think, oh, well, there's always something to discover. But the periodic table really is an amazing achievement of mankind, that we really do understand the building blocks of the universe. Lithium really is the best anode material. So you can make a battery with sodium, no problem. Right, for sure. It's just going to be 3 times as heavy and maybe 85% the voltage, which means you end up with about a 40% energy density. That for stationary applications, probably kind of fine. And lithium and sodium's a lot cheaper. So I think for grid storage, it's no problem. I don't think we're going to have material shortcomings. No problem's not quite the right way to say it, but we won't. Material limitations won't be a serious governor on grid storage applications, or even potentially large format transportation. Right. So if you think about buses or trucks, where the weight of the battery is a relatively small weight of the overall vehicle, then
rail.
Yeah, for sure. Well, because you hardly need batteries, right? You power it right through the right through the rails. But so those are elements where those design constraints aren't as important. For light duty vehicles, for personal electronics, and for aircraft, energy density is all important, and that's where lithium is just second to none, and the drop is just gargantuan. On the cathode side, it's a little not quite as clear a picture, but it's still a pretty clear picture. And the picture is that nickel, that cobalt's the best if you don't care about price. Nickel is a really strong second, and some blends of cobalt, nickel, and other elements, whether it's aluminum or manganese or even other things, tend to perform really well. So you can just think of nickel, cobalt as a package there, and they kind of titrate each other based on price and performance for the specific application. But if you go to the next best material, let's focus on iron phosphate because it's in wide use. Iron phosphate's a great cathode material. Why do I say that? I say that because iron is super cheap, as we all know. What is it about? It's about 3 orders of magnitude cheaper than nickel or cobalt, right? 2.5. It's way, way, way cheaper. So that's great, and you're not going to have it's the most common element, most common metal in the Earth's crust. You're not going to have any problems with supply at all. But when you have an iron phosphate battery, let's really nerd out here for a second, if you will, Shayle. So cobalt. So a nickel oxide battery is nickel NiO2. So one nickel element one nickel atom and two oxygen atoms. Okay, iron phosphate is Fe, iron, PO4. So iron, one iron, one phosphorus, and four oxygen atoms. Now, the voltage or the energy you get per electron is about 70% as high as in the case of nickel or cobalt, like a 40% reduction in maybe 30% reduction in the voltage. I can't quite remember. But now you have to add to that, and that's that formula, FePO4. That's how those are the atoms that react with one lithium. Okay, so whereas the NiO2 or COOO2, so cobalt oxide, those are the elements that react with one lithium atom. So in order to react with one lithium atom in iron phosphate, you need an extra phosphorus that you didn't have before. You need two more oxygens that you didn't have before. And so that's three new atoms that all add weight, and the voltage is lower. So you end up with 40% the energy density, something like that. So that's terrible. Now, why is it good? It's good because it actually has really long cycle life. It's a very, very, very stable crystal. So you can think of it as cycling it thousands of times with very little degradation. It just weighs more for the amount of energy. So it works great for a stationary application. I think it probably will be the go-to for large format transport, probably like buses, city buses, things like that, where acceleration is not that important. And the vehicle's really heavy already. But if you swap that out, all things being equal, you swap out an iron phosphate battery or an NMC, nickel manganese cobalt battery in a standard EV and with an iron phosphate battery, you're going to lose a lot of range. You're going to lose a lot of acceleration. You're going to add a lot of weight. It's bad all the way around. It's much less good. You wouldn't want it, all things being equal. It might be cheaper. It is cheaper. It is, but the cost reductions aren't that great, actually, believe it or not, for a variety of reasons. But you save a little bit of money, performance goes way, way down.
Yeah, so you see a lot of LFP batteries and EVs in China for like lower end vehicles, lower cost, good durability, lower range as a result. And you're starting to see a little bit more of it here, but certainly not in the high end models and not for the like long range batteries. We should talk for a minute about recycling, because there's been a lot of attention paid and excitement around battery recycling and getting some of these minerals out of used EV batteries to recycle into new EV batteries. What portion of that future demand do you think can be taken up via recycling?
Yeah, so this is, if we take the longest view here, this is maybe one of the really exciting things about the energy transition is that the renewable energy economy is going to give rise to the circular economy, right? And it's really, really exciting. The fossil fuel economy fundamentally can't be circular. Take fossil fuels out of the ground, right? It's carbon and hydrogen. You burn it in oxygen to make CO2 and water. The CO2 goes into the atmosphere and it stays there for tens of thousands of years. You're not going to get it back, despite what a bunch of people say. You will not get it back.
I was going to say, I know your opinions on direct air capture. We've had separate conversations on that.
It's an utter waste of time. Totally absurd technology that will cost. That is a staggering waste of human brain cells and capital and resources. And we should be we should always be working on the most effective, the best marginal use of our capital. And the best marginal use of our capital is not to do really expensive things like direct air capture, or even worse, trying to direct air capture and then converting fully oxidized carbon reducing it all the way back down to fuel. It's fun to think about. It's not going to happen for decades, and people shouldn't waste their brain cells on it. I'm sure I just angered a lot of your audience, but I wanted to slip that in. But back to the point. It is a one-way economy. Fossil fuel economy is a one-way economy, right? And that's the problem. The CO2 just accumulates in the atmosphere. The renewable energy economy, the batteries, the energy doesn't come from the batteries. The energy comes from other sources. The batteries are necessarily reversible, and which is the whole game. We can achieve we can achieve 90, 98, 99% recycling rates on these batteries. And over time, we'll get to the point where we do not have to mine them, which is really, really exciting. But that will take more than a generation, unfortunately. We need a lot more materials in the system now. You can't recycle metal until you have it, right? And so we need to get enough metal into the system that we can get to sort of a steady state circular economy, and that will happen. But it'll take 50 years maybe. But it's really exciting. It's really exciting that we can actually we can move past an extractive economy. It'll just take some time.
Yeah. So to explain why it'll take 50 years, in part, it strikes me that there's probably two challenges to recycling comprising a significant portion of the demand over the next couple of decades. One is just the growth trajectory, right? So you're going to be recycling the stuff that we used 10 years ago or however many years ago. But in the meantime, we're just going to have tons more demand for all this stuff, literally tons, but actually megatons.
Right. Yeah. I mean, just do a simple thought experiment, right? Let's say there's 100 cars in circulation, and let's say there's 1,000 potential car owners, right? So all those cars retire. You can recycle them into another 100, but you need 900 more to get all the people there, right? And so where do you get the metal for those 900? Well, you have to get it out of the ground, and you have to mine it all. But once you get to 1,000 cars, if you had a population of 1,000 car owners, then you'd be more or less in steady state.
Right. Not to mention that assumes you get the full 100 back for 100 more vehicles when you do the recycling, which we're not there yet.
Yeah. I mean, we're not there yet, and that's an economic consideration, right? There's technically you can get nearly 100% for sure. There's no, the atoms are conserved, right? Atoms aren't destroyed in the process. There's no nuclear reactions that occur in batteries. But it's just a cost. It's just a cost optimization, and currently, it's heavily a function of the. It's a function of the commodity. So it's a function of several things. It's a function of the commodity price. So like the value, how worth it is it to extract the material from the, from the old car, the old battery. How much it costs to recycle, how much it costs to do the process, right? And so if you have, like in your iPhone, you actually have several dollars worth of gold in your iPhone. All that gold gets recycled if you turn in your iPhone back to Apple. For a long time, they weren't recycling the lithium. I think they are now. For a long time, they weren't because the cost didn't pencil out. But it wasn't a technical problem. And as you switch to car batteries, the recycling case gets higher because it's better. It's more attractive to recycle because the aggregation costs are a lot lower. You get so much more metal per car that ends up being very favorable to the economics.
I want to talk for just a minute about geopolitics. I mean, you've mentioned this a couple of times, but we've got Russia as a key player in some of these minerals, China as a key player in other minerals. As we, there's been some talk about like as we transition from a fossil fuel-based economy to an electricity-based economy, or at least partially electricity-based economy, like are we introducing just a new, different set of geopolitical challenges where our reliance on the Middle East has waned, but now we've become reliant on a new set of countries? I know this is sort of central to what you guys are doing at Cobalt. What do you think are the prospects for North America and Europe in particular to be able to domesticate the key mineral production for most of the stuff we're going to need?
It's a great question, and it's an interesting. It's not a perfect analogy. The best reason it's not a perfect analogy is actually because of the recycling component, right? Because you move toward a circular economy, you become less and less dependent on whatever the jurisdiction is that you're importing the product from. So sort of just like from that first order look, it's better, all things equal. But because we're not at the circular level there, there's still this transitionary period where you certainly have to source materials from wherever you can get them. The outlook for the outlook for what's broadly referred to as the West, right? So North America, Japan, Australia, the EU, is pretty strong. North America has tremendous potential for nickel, cobalt, and lithium in particular, and fairly meaningful for copper. The largest copper mine currently in development is in Arizona, for instance. Not yet producing, but close to producing. Or it's among the biggest. I'm not sure it's absolute biggest. It's very, very big. There's Australia is a major mining jurisdiction with tremendous potential. That's really positive. We mentioned the two most salient challenges here are Russia and the DRC, Democratic Republic of Congo, particularly where our reliance on cobalt from the DRC. That's probably the most salient reason you've seen such a push toward nickel-rich batteries, which means you're trading off nickel for cobalt, pushing down cobalt, pulling up nickel, is price, which we've mentioned, but also just security of supply, just being reliant on nickel. Nickel's produced by dozens of countries. The largest producer is less than a third of production, whereas cobalt has 2/3 in
and
Congo.
human rights concerns too, right? Congo.
For sure.
I mean, you alluded to it, but
for sure.
There's a real reason to get off of reliance on cobalt from Congo.
For sure, no, absolutely true. Congo is a very difficult jurisdiction. They've had in 2000. They had a civil war that ended in 2004, and in the previous 5 years, there were more people killed in that war than in any other conflict since the Second World War globally. It was a very troubled jurisdiction. A lot of the north is controlled by warlords, and there's been an acute challenge with child labor in the mines. Not at the major mines controlled by international mining corporations, but at what's so-called artisanal mining. There's cobalt that comes right on the surface in cobalt in the form of cobalt oxide that people can sort of dig up, and so these small time operations just get created to make little pits of cobalt, and that's been a big problem. Something like 15+% of cobalt that's been estimated coming out of Congo is sourced in that manner. So it has a big spotlight on it, and there is some positive developments. The Congolese are working on it, but it's still a very serious problem for sure.
Okay, final question for you, and then I'll let you go. As you look forward here, what do you think is going to be, which of these metals or what sort of process is going to be what's the governor of growth? What's going to be the constraint more than anything else?
It's a really good question. The two that I think, let me answer the question this way. I'll say are Cobalt's priorities, commodity priorities, the things that we are trying to find the most. And I mentioned discoveries a couple times before. Let me explain what I mean by that. So discovery is the source. We don't know where the deposit is yet, right? So there's plenty of deposits that are out there that are known but are not producing. And so there's a lot of effort to get those into production, and that's chiefly the province of the major mining, existing major mining houses and other companies, conglomerates that are trying to get those into production. There's strong market forces to do that. There's the question is what comes after that, right? What fills that pipeline? That's where discoveries come in. So that's a brand new. We literally don't know where it is. So let me tell you some really bad news, and let me tell you some hopeful news. So the really bad news is that the industry has been getting worse and worse at making discoveries, new novel deposits that were not previously identified, worse and worse for over a generation. Something we've dubbed Eroom's law of mining. Eroom is Moore's law backwards, right? So it's getting worse and worse the more you spend. And it's down about a metric that we've defined as exploration effectiveness, so the number of tier 1 or tier 2 discoveries made per dollar of exploration expenditure has dropped about sixfold in the last 30 years. So you spend the same amount of money, you'll find 1/6 as amount of stuff.
Is it pretty simple? We've just picked the lowest hanging fruit, and so we're just climbing up the tree, basically?
So there's two components to that. That is the first order a problem for sure. The easy things have been discovered. But you might ask, what is an easy thing? Well, an easy thing is actually well defined. It's something that's sticking out of the ground. So it's there's an outcrop, and a skilled geologist can walk up to it and look at it and say, those are ore minerals, and we should explore this outcrop. We should drill here. We should dig here. We should whatever, because there could be something. That's Or the second would be just a geochemical anomaly. You're looking for copper and you're measuring soil, copper in soil, and sure enough, you find a 10x increase in copper in a particular soil sample, and you think, oh, that's interesting. What's below this soil? Those are the easy things. The inventory of those easy things has been largely cold. So the second component to Eroom's law, so that alone doesn't quite give you Eroom's law, right? Because fastballs in the Major League Baseball keep going up, right? But batting averages don't really go down. Why? Well, because batters get better as pitchers get better, right? And so if you were investing in technology, right, and getting better at finding things, not at the surface but at a few hundred meters deep with all kinds of new technologies, then you would be balancing this. The learning curve would balance the depletion of the supply curve, right? But that hasn't happened. The industry has chronically underinvested in exploration writ large and exploration technology in particular, which is a real problem. And so that's what we're trying. That's the void we're trying to fill, which is investing really, really heavily in R&D and new approaches to discover these things that aren't the easy things to see. But I want to make sure I answer the question that you started with, which is what's going to be the governor on all of this? Like what commodity is the most important? And I was going to basically force rank how we think about it. So we would order it in the following way. We'd order it as nickel, followed by lithium, followed by cobalt, followed by copper. And they're all crucial. They're all really important. Taken in sort of reverse order, lithium, copper has the biggest existing market, and is the most recycling will have the most impact in the nearest term, and expansions to existing mines can have the most impact in the near term. The other three are in different categories. Nickel, we put one because there's a huge supply of nickel and laterites, but it's much higher cost and it has much bigger sort of local impacts. And we're worried that if all the supply goes the way of nickel laterites, there will be a lot of resistance to more development. The types of deposits that we're focused on are called nickel sulfides, which are much lower cost to produce and much lower impact locally. They're just much harder to find. That's the problem. But if we can find those, we can really bend down the cost curve.
All right, we could go on for hours, but we are not going to. Kurt, this has been incredibly informative, and I would welcome the opportunity to talk about it again and get even deeper on battery chemistries next time. But thank you.
Awesome, Shayle. It's great to be here.
Kurt House is the CEO of Cobalt Metals. This show is a co-production of Postscript Media and Canary Media. You can find the show on Twitter at @CatalystPod, and you can also find me, Postscript, and Canary there too. Don't forget to send in your questions for the Ask Me Anything mailbag episode. Just tag us with the hashtag AskCatalyst on Twitter or on LinkedIn. And send us feedback. If you like the show, go over to Spotify or Apple Podcasts or wherever you get the show and leave us a rating and review, or just share the episode with a friend. You can find links for this episode's topic and guest in the show notes on canarymedia.com. Postscript is supported by Prelude Ventures, a venture capital firm that partners with entrepreneurs to address climate change across a range of sectors. Quite a range, one might say, including advanced energy, food and agriculture, transportation and logistics, advanced materials and manufacturing, and advanced computing. That is a range indeed. The producers for this episode were Daniel Waldorf, Delvin Abuaji, and Stephen Lacey. Mixing by Greg Vilfrank and Sean Marquand. Theme song by Sean Marquand. I'm Shayle Khan, and this is Catalyst.